All right, in this section, Chapter 11, Section 7, we are going to be covering a summary of all of the tests for convergence that we've done before. So this is going to be similar to the section on integrals, where we learned all of our integration techniques and then we had to select the appropriate integral or technique of integration in order to do the integral. All right, so 11.7, we're going to be talking about tests for convergence and divergence. So determine if the series converges or diverges, and state the test that is used and show any supporting work. So when we're trying to work a problem like this, the first thing that we want to do is determine if we think it's going to converge or diverge. So by looking at this series, if we analyze both the numerator and the denominator, the numerator is going to have degree 1, so that's order 1, and the denominator is also going to have degree 1, so it's going to be order 1. And if we divide each of those, we're going to have degree 0. So if we have a degree 1 divided by a degree 1, we're going to get a constant. And if we keep adding a constant, we will probably end up with something that diverges. So our guess is that this series is going to diverge. So if we look at our list of tests, one of the best ones, especially if we think something is going to diverge, is to try the test for divergence. So remember, this test does not tell us if a series converges ever, but it can tell us when they diverge. And it says to use the test for divergence that we take the limit as n goes to infinity of the a sub n's, and if it's not equal to 0, then the series diverges. So in this case, our a sub n's are going to be n minus 1 over 2n plus 1. So if we take the limit as n goes to infinity of our a sub n, we factor in n out of both the numerator and denominator. And factor our n out. And that leaves behind 2 plus 1 over n. And our n's reduce out. So if we take the limit now as n goes to infinity, constant over infinity goes to 0, constant over infinity goes to 0. So our limit converges to 1/2, since the limit of the ANs is not 0, by the test for divergence, the series diverges. So let's kind of recap. So for our first example, we wanted to determine if this series converged or if this series diverged. So we looked at it, and since we had order 1 divided by order 1, which would be a constant, we guessed that it was going to diverge, so we used the test for divergence. And we indeed took our limit and got 1/2, so according to the test for divergence, if the limit is not equal to 0, then the series did indeed diverge. All right, let's take a look at our next example. So if we take a look at B, we've got the sum as n goes from 1 to infinity of the square root of n cubed plus 1 over 3n cubed plus 4n squared plus 2. So once again, we want to determine whether or not this converges or diverges. So let's do a little bit of analysis first. So we have a square root and an n cubed. So if we just analyze the leading term here, we would have the square root of n cubed would be the same as n to the 3/2 power. And if we analyze our leading term here in the denominator, the order is going to be n cubed. So n cubed, so n to the 3/2 divided by n cubed, if we subtract their exponents, 3 take away 3/2, 3/2 is 6/2, we're going to get 1 over n to the 3/2. So the order of this ratio is going to be about this, and that is 1 over n to the 3/2. So what we would want to do is try limit comparison with a p-series of 1 over n to the 3/2, which was the order of the ratio. So now, if we go and look at our sheet here, if we try limit comparison, we have the following. So our limit comparison test says if the ANs are all bigger than 0 and the BNs are all bigger than 0, and the limit as n goes to infinity of AN over BN equals C, which is greater than 0, then either both series converge or diverge. So in other words, they share the same fate. So we want to compare that with a p-series of the form 1 over n to the 3/2. And once again now, if we look at our sheet here for p-series converge if p is bigger than 1. So we have 1 over n to the p. Our p is going to be 3/2. So that is going to give us a convergent series to compare with. So this guy is our p-series, and our p is 3/2, which is bigger than 1. So then this guy is going to converge. So we're going to do our limit comparison with a convergent p-series. So our limit comparison test says if the ratio of the sequence members converge, since this converges, both will converge. So our ANs then are going to be, from our series here, so we have the square root of n cubed plus 1 all over 3n cubed plus 4n squared plus 2. And then our BNs are going to be our convergent p-series, so 1 over n to the 3/2. And we take the limit as n goes to infinity of the ANs over the BNs. So that gives us square root of n cubed plus 1 over 3n cubed plus 4n squared plus 2 divided by 1 over n to the 3/2. And When we have a fraction divided by a fraction, we multiply by the reciprocal. We're going to have the limit as n goes to infinity of the square root of n cubed plus 1 over 3n cubed plus 4n squared plus 2 times n to the 3 halves over 1. So now we're going to factor the highest power out of each of these. So in doing so, we have the limit as n goes to infinity. And if we take our n cubed out there, we have an n cubed, and that leaves 1 plus 1 over n cubed times n to the 3 halves. And then in the denominator, we factor out an n cubed, and that leaves behind 3 plus 4 over n plus 2 over n cubed. So the square root of n cubed is really just n to the 3 halves. N to the 3 halves times n to the 3 halves is n cubed times the square root of 1 plus 1 over n cubed over n cubed times 3 plus 4 over n plus 2 over n cubed. So finally, our n cubes reduce out. I left off my limit. The limit as n goes to infinity. So then as n goes to infinity, that goes to 0, that goes to 0, and that goes to 0. So my limit converges to 1/3. So now when we look at our limit comparison test, what we were checking is the limit of the an's over the bn's equal to some number that is bigger than 0? Check. 1/3 is bigger than 0. So by limit comparison, the series converges. All right, let's take a look at our next example. So we have our series as n goes from 1 to infinity of n times e to the negative n squared, and we want to know if this converges or diverges. So when we look at our series, our an's are n e to the negative n squared, which if we move that exponent from the numerator to the denominator because it's negative, we would get e over n squared. So it looks like the limit as n goes to infinity of the an's is going to be, well, that's type infinity over infinity. So if we use L'Hopital's rule, the derivative of n is going to be 1, and the derivative of e to the n squared is 2n e to the n squared, which is a constant over infinity, which gives us 0. So this tells us pretty much nothing, because what we just ran was the test for divergence. And it says the series diverges if that limit is not 0. So remember, if it equals 0, it doesn't tell us it converges. It doesn't tell us anything. So the test for divergence the test for divergence gives no information. All right, so we need to come up with a different test. So we look at our sheet of tests, and we have something of the form n times e to the negative n squared. And we know that the exponential is going to dominate a polynomial. So we think that this should converge. And it's not a p-series, it's not geometric, but our an's are all positive, and since the en's, e to the negative n squareds, are going to dominate, it is going to be increasing. So the integral test may be helpful. So our integral test states the following. If our an's are positive and let an equal f to the n, and if the integral converges, then the series converges. If the integral diverges, then the series also diverges. So to use the integral test, we would need to integrate from 1 to infinity of n e to the negative n squared dn. So to do this integral, we would need to do a u substitution. So if we let u equal negative n squared, then du is equal to negative 2n dn. And changing our limits of integration, u of 1 is going to be negative 1 squared, so that gives us negative 1. And u of infinity would be negative infinity squared, which is going to be negative infinity. So our new limits of integration would be from negative 1 to negative infinity of n e to the u, and then solving this for dn, we would divide by negative 2n, divide by negative 2n. So dn equals negative du over 2n. So we get du, negative du over 2n. So our n's reduce out, and we get a minus sign that goes out in front. So we would get the negative of the integral from negative 1 to negative infinity of e to the u du, which is going to be the same as reversing our limits of integration, the integral from negative infinity to negative 1 of e to the u du. So now our antiderivative of e to the u is e to the u evaluated from negative infinity to negative 1. So that gives us e to the negative 1 minus e to the negative infinity, which is 0. So we get 1 over e. Just kidding. I lost a 1/2. So we get 1 over 2e. That's much better. Regardless of whether it was 1 over e or 1 over 2e, our integral is still going to be the same. Which is, by the integral test, our series converges. So, by the integral test, the series converges. All right. So, it's been me working for a minute. I've done the first 3. Now it's your turn. So let's go ahead and get a U-try set up. So our U-try is the sum as n goes from 1 to infinity of 1 over 2 plus 3 to the n, and we wish to determine whether or not this converges or diverges. So I'll go ahead and... So to do this U-try, we might notice that our a sub n is 1 over 2 plus 3 to the n. And that looks kind of like a geometric. So if we were to look at b sub n being 1/3 to the n, or 1 over 3 to the n, these things are almost exactly the same, other than I'm adding 2 to the b sub n. So since this looks almost geometric, we will try limit comparison with our bn equaling 1 over 3 to the n, which is the same as 1/3 to the n. So this is a convergent geometric. So we take our limit as n goes to infinity of 1 over 2 plus 3 to the n all over 1 divided by 3 to the n, which is the limit. So a division of a fraction we can multiply by the reciprocal, gives us 1 over 3 plus 2 to the n. I'm going to write it in the other order, and then 3 to the n over 1. And so that gives us the limit as n goes to infinity of 3 to the n over 3 to the n plus 2. And if we factor out our 3 to the n from both the numerator and denominator, that's going to leave us 3 to the n times 1 in the numerator, and we factor out a 3 to the n times... Here we're going to have 1 plus 2 over 3 to the n. And our 3 to the n's reduce out. And then as n goes to infinity, a constant divided by infinity goes to 0. So then our limit converges to 1 over 1, which equals 1. So then by limit comparison, the series converges. All right. Let's keep on going. All right, so now this time we have the sum as n goes from 1 to infinity of negative 1 to the n cubed divided by n to the 4th plus 1. So we want to determine if this series converges or diverges. So we look at it, And we notice that we've got this part right here. So the negative 1 to the n is going to make this series alternate. So the factor of negative 1 to the n makes this an alternating series. So we go to our sheet and we look for our alternating series test. So since we have an alternating series, we can verify that it satisfies the alternating series test, and if so, then we will know that the series converges. So the alternating series test says if one of an and an plus 1 is positive and the other is negative for every n, and a to the n plus 1 is less than a to the n, and the limit as n goes to infinity of the n equals zeros, then the alternating series converges. So we need to show that it is decreasing and always positive. Well, the always positive is easy because the n cubed is a positive, n to the fourth is a positive, so a positive plus a positive is positive, and a positive divided by a positive is positive. So that part is done. And to show it is decreasing, we can compare it to its continuous counterpart. So we have f of x equals x cubed plus x to the fourth plus 1. And if we take the derivative, f prime of x is going to be, here's my f, here's my g, so it's g f prime. So x to the fourth plus 1 times f prime, which is 3x squared, minus x cubed, so fg prime times 4x cubed, all over x to the fourth plus 1 squared. So now let's clean this up a bit. So our f prime is going to be 3x to the sixth if we distribute this in, plus 3x squared minus 4x cubed all over x to the fourth plus 1 squared. So now, sorry, I have a typo here. I wrote the third power times the third power makes this the sixth power. Collecting our like terms, we would get negative x to the sixth plus 3x squared all over x to the fourth plus 1 squared. If we factor out a GCF of negative x squared, we would have negative x squared times positive x to the fourth minus 3 all over x to the fourth plus 1 squared. So for x greater than or equal to 2, we're going to get this term will be negative always. This will be positive and a positive. So a negative times a positive divided by a negative means it's going to be negative. So we have f prime of x is less than or equal to 0 for x greater than or equal to 2, which means f of x is decreasing for x greater than or equal to 2 because the derivative tells us about the slope, but f of x was really just our a sub n. So a sub n equals n cubed all over n to the fourth plus 1 is decreasing for n greater than or equal to 2. So we've now satisfied our decreasing, and the only thing we have left to show is we need to show that the limit of the an's is equal to 0. So it's decreasing, and if we take the limit as n goes to infinity of the -1 to the n cubed all over n to the 4th plus 1, if we factor out an n to the 4th from the denominator, we have n cubed in the top times -1 to the n all over n to the 4th times 1 plus 1 over n. That's going to reduce to -1 to the n all over n times 1 plus 1 over n. And if we take the limit as n goes to infinity, that goes to 0. But then this whole thing, a constant divided by infinity, the whole limit goes to 0. So we could also analyze that we have a degree 3 over a degree 4, so that limit would have to be 0. So by the alternating series test, the series converges. All right, let's take a look at our next example. So we want to determine if this series converges or diverges. So since we have a factorial and an exponential, this one really says try the ratio test. And the ratio test is a very powerful test. If you're not sure what to do and you just need to pick a random test to get started, the ratio test is always a good first pick if you don't know what to do. The ratio test would have worked on, it wouldn't have worked on E, it would have worked on D, it maybe, yeah, you could have made it work on C, it would have been a little bit of work. And it wouldn't have worked on B, and it wouldn't have worked on A. But it is a pretty good test to try, especially if something has factorials. So we have our A sub n, or sorry, in this case, our A sub k. Our series is indexed on k. So 2 to the k over k factorial. And the ratio test says the following. So to use our ratio test, we're going to have our series converges absolutely if the limit as n goes to infinity of the absolute value of an plus 1 over an is less than 1. It diverges if the same ratio is greater than 1. The ratio test unfortunately fails if the limit is equal to 1. These are the same three things that happen with the root test, but instead of a ratio, we're going to have a root there. So we need to calculate the limit as n goes to infinity of a to the k plus 1 over a to the k in absolute value. So that's going to be 2 to the k plus 1 over k plus 1 factorial all over 2 to the k over k factorial in absolute values. We can drop our absolute values because all of these terms are positive. So dividing by the reciprocal of the denominator, we're going to have 2 to the k plus 1 all over k plus 1 factorial times k factorial over 2 to the k. We can use our properties of exponents to rewrite two to the k plus 1 as 2 to the k times 2, because we're using our exponent property x to the n times x to the m equals x to the m plus n, but we're just using it backwards, over, and then same thing, we can expand our factorial and write this as k plus 1 times k factorial using our definition times k factorial over 2 to the k. So then our k factorials reduce out and our 2 to the k's reduce out, and we're just left with the limit as k goes to infinity of 2 over k plus 1. Well, that's a constant divided by infinity, so that is equal to 0. 0 is less than 1, so the series converges absolutely. By the ratio test. All right. So example 2 says determine the values of x so that the series converges. Don't forget to check the endpoints. So we want to determine the values of x so that this converges. So whenever we have something of this form where we're finding the values of x where something converges, we will almost always use either the ratio test or the root test. So let's go ahead and try the ratio test. So our a sub n is going to be negative 1 to the n, x to the n, all over 2n plus 1. But we're going to be doing the absolute value of this. So when we take our limit as n goes to infinity of the absolute value of a to the n plus 1, we're going to have a negative 1 to the n plus 1 times x to the n plus 1 all over 2 times n plus 1, all divided by just our regular a sub n, negative 1 to the n times x to the n all over 2 to the n plus 1. So we're still taking our limit as n goes to infinity, and we're going to multiply by the reciprocal. While I'm doing that, I'm going to use my properties of exponents to break some things up. So I'm going to have negative 1 to the n times negative 1, x to the n times x over, distributing my 2n, I'm going to get 2n. 2 times 1 is 2, plus 1 is 3, so I get 2n plus 3 times the reciprocal of the denominator, which is 2n plus 1, all over negative 1 to the n, x to the n. So now a whole bunch of things are going to reduce out. Those guys reduce out, my x to the n's reduce out, and the absolute value of a factor of negative 1 is going to be positive 1 by absolute value. So multiplying by a positive 1 isn't going to change anything. So I have the limit as n goes to infinity of now let's do it this way. The absolute value of -1 over times 2n plus 1 over 2n plus 3 times the absolute value of x. So we just split this up, and if we factor our greatest common factor out of each of these of n, we have an n over an n, and then that's going to leave our -1 times 2 plus 1 over n divided by 2 plus 3 over n times the absolute value of x. So if we take the limit as n goes to infinity, those go to 0, those go to 0, those cancel out. So then this converges to -2 over 2, which is -1, but the absolute value of -1 is 1. So this limit then just equals the absolute value of x. But if we go back and look at our ratio test, which is what we were using, we were asked to determine for what values of x does this series converge. Well, by the ratio test, this series converges if this limit in absolute value is less than 1. Well, this is the limit. So for the series to converge, the absolute value of x must be less than or equal to 1. So in other words, we have to solve the following inequality. The absolute value of x is less than 1. Well, this is a pretty simple absolute value inequality. So the interval of convergence or the radius of convergence, sorry, is -1 to 1. But then we were given this hint. It says don't forget to check the endpoints. So when we have an x involved, remember we solve for when this was less than or equal to 1. The test fails when x is equal to when the ratio is equal to 1. So the ratio will be 1 or -1 at x equals -1 and 1. And so what I mean by that is we actually have to put in x equals -1 into our original series. So if I put -1 in for x, my series becomes the sum as n goes from 0 to infinity of -1 to the n times my x value, which is -1 raised to the n, because that's my x, all over 2 to the n plus 1. So then -1 times -1 to the n is going to be, we multiply two things with the same base, we add their exponents, so that's -1 to the 2n. But -1 to the 2n is always going to be an even power, so that's going to be 1. So we're going to end up with 1 over 2 to the n plus 1 for our a sub n. So that gives us that our series is going to become n equals 0 to infinity of 1 over 2n plus 1. So let's do limit comparison. With 1 over n, which is the harmonic, which diverges. It also diverges as p series with p equal 1. So if we take the limit as n goes to infinity of 1 over 2n plus 1 all over 1 over n, it's the same as the limit as n goes to infinity of 1 over 2n plus 1 times n over 1. Factoring out our n, we have 1. We factor out our n, we get 2 plus 1 over n. And as n goes to infinity, that goes to 0. And those reduce out. So our limit equals 1/2. So since the harmonic diverges, this diverges. So the series diverges at x equals -1. Now we have to check the other endpoint, which was +1. So if we put in x equals +1, we would have the series, the sum as n goes from 0 to infinity of -1 to the n times, we're replacing x with 1 to the n all over 2n plus 1. Well, 1 to any power is going to be 1, so this just reduces to the sum as n goes from 0 to infinity of -1 to the n over 2n plus 1. And that's going to be an alternating series. So our an is -1 to the n over 2n plus 1, which is going to alternate and decrease. So by the alternating series test, the series converges at x equals 1. So the interval of convergence is, it does not converge at -1, but it does converge at +1. So we get a half open interval from -1 to 1. So then the x values for which this series converges are for all x's from -1 to 1, including +1, but not including -1. All right. So now it is your turn. So for your U-try, I would like you to do this problem, but I don't want you to check the endpoints. Just find the interval without the endpoints where this converges. And to give you a hint, I would try the ratio test again. All right. So to do this example, what we're going to do is the ratio test again. So we're going to take the limit as n goes to infinity of a sub n plus 1. So that's going to be negative 2 to the n plus 1 x to the n plus 1. All over 3 to the n plus 1 plus n plus 1 all over negative 2 to the n x to the n 3 to the n plus n in absolute value. So once again, taking the reciprocal of the denominator and multiplying and expanding using our exponent properties, we're going to have negative 2 to the n times negative 2 x to the n times x all over 3 to the n times 3 plus n plus 1 times our 3 to the n plus n all over negative 2 to the n times x to the n. And once again, a whole bunch of stuff reduces out: the negative 2 to the n, the negative 2 to the n, the x to the n, the x to the n. And let's rearrange some of these things. So we have the limit as n goes to infinity, and I'm going to factor a 3 to the n out of the numerator and denominator. So 3 to the n, and that's going to leave behind a factor of negative 2 times, and then I'm going to have 1 plus n over 3 to the n in the top, and doing the same thing in the denominator. If I factor out a 3 to the n, that's going to leave behind a 3 plus n over 3 to the n plus 1 over 3 to the n. And then our 3 to the n's reduce out. And if we take the limit as n goes to infinity, an exponential beats a polynomial, so that goes to 0, 0, and 0. You can use L'Hopital's rule if you wish. So then our limit becomes the absolute value of negative 2 over 3, which is, I lost my x. There it is. And we'll just put it here, times the absolute value of x. So we get 2 over 3 times the absolute value of x. And this has to be less than 1. So we have 2 over 3 times the absolute value of x is less than 1, gives us negative 1 is less than 2 over 3x is less than 1. So to isolate x, we multiply everything by 3 over 2. By 3 over 2 and by 3 over 2, and that gives us negative 3 over 2 is less than x is less than 3 over 2. So that gives us our interval, and then we would have to test the endpoints to get convergence